Nuclear reactions and half-life. All right, so what is this half-life all about? Now, we have a concept of nuclear reactions if you've been studying, okay, and watching the videos, okay, on this channel. Okay, I can put up a link to the nuclear reactions up above there. Here's a summary of alpha decay, beta decay, electron capture, etc. So you have these particular nuclear reactions happening. Now, one of the neat things that we can do is we can obviously apply quite a bit of math towards physics. And one concept, which is the half-life concept, actually does come from mathematics, and it comes from exponential decay. Now, I'm going to assume that you know a little bit about exponential functions, okay? And you kind of have seen maybe a little bit about half-life already. So I'm going to be applying that concept to nuclear reactions in this video. If you want to be able to see half-life and get a little bit more exposure to it, both from the mathematics viewpoint, okay, and kind of get an intuitive idea, I'll put up a link up above there to a video which actually goes over a half-life from the viewpoint of math, which is typically a grade 11, okay, or possibly even grade 10 topic. So let's dive in. So we have all of these different nuclear reactions happening. Now, one of the major things that you notice in all of these, okay, so from alpha and beta decay in particular, so you notice that the parent, okay, so whatever the parent might be, turns into a daughter nuclide or a daughter atom that you have, and you see this all over the place. So a parent basically changes back into a daughter, okay, so parent, daughter, okay, and you see this happening, maybe except the gamma decay, okay, which is something a little bit different. But in all the rest of them, so alpha and beta and electron capture, you have that an original kind of atom that you have, it starts to change its nucleus, right? So for various reasons. Now, that particular change that you have means that it is undergoing, okay, some kind of a change into something different. Now, here is an example, okay, that I want to point out, and we'll touch base on this example. So for example, here you have a beta negative, okay, where the electron kind of gets shut out, okay, and the carbon changes into a nitrogen. And as you can see there, so the number of protons changes. And what I want to do first is I want to concentrate on this actual carbon itself. And I want to let you know what all of this half-life related to nuclear reactions is all about. So if you take carbon, you will start with a certain amount of that carbon. So you're going to have a certain mass. Let's call this the initial mass of the carbon that you have. Maybe it's 1 gram, maybe it's more, all right? So it doesn't really matter. And as you can see, this thing, okay, continuously is changing. So that means that what you have is the number of carbon, okay, so the actual amount of carbon in mass keeps on decreasing. So this side keeps decreasing in mass, okay, in terms of the amount of carbon that you have. And what is increasing in mass is the nitrogen. So this is actually increasing in mass as you're going through. And eventually, so as you keep going, right, so as you go through this nuclear reaction, because of the fact, okay, that it is a nuclear reaction, which is kind of spontaneously occurring, so without necessarily any external triggers, then what you have is that the carbon continuously changes. Now, if it continuously changes, the amount of mass that it has will get less and less and less. Now, what that is called, okay, so as you're moving along from a certain amount, okay, and decreasing the amount of mass, well, that means the amount of actual carbon is decaying. So it is decaying, and notice that we do call it decay, right? So in all of these items, right, so it's alpha and beta decay actually have the word decay in it. And within here, so that particular decay causes less and less, in this case, carbon or any other, okay, radioisotope that you might have that is changing along. So what we are interested in, and it's very nice to be able to capture this, if we notice that this, okay, process of whatever you're starting initially with in terms of mass, okay, gets to the point where the amount of mass is equivalent to half of what it has started. So maybe you started with certain amount, okay, so let's say, you're starting with 100%. Now it doesn't matter, okay, if it's 100 grams, 1 gram, 5 gram, let's just call it 100% in the beginning of whatever carbon you had. And now it gets to 50%. So what you notice is that it basically has decayed by 50%. And now the amount of time that it takes for this 50% decay, okay, is referred to as the half-life time of that particular atom that we have. So this is what we are referring to as half-life time. Now that half-life time can be designated in many ways. So, I wrote it T with 50% at the bottom. Okay, half, which you can write as half in this particular way. Okay, you might see it as T with an H for H, which is just half-life, or you might just see it as H. All of these just mean how much time does it take for this particular atom, okay, or this amount of mass to decay by 50%. And now various different atoms that you have a different decay constant. So this is the decay constant that we are trying to figure out. So that constant, okay, will depend on what exactly, okay, is happening in the nuclear reactions. So if you want to know, okay, what this is, this carries on, okay, through 50%, and then it can carry on another 50%, it can just keep decaying. And what you notice is it's an exponential decay that exponentially kind of goes through. So if you had this on a timeline, and as you were going through in here, so what you would have is you would start with 100% of whatever it is that you're dealing with. And then at 50%, okay, so if you get to 50%, that would have been referred to as one half-life. Now, when you get to 25%, okay, of what you started off with, well, 25% is half of 50%. So therefore, that's another half-life. So this would have been one half-life. This is another half-life. And then it would get to 12.5%. And this would continue on, okay, as you're carrying through. Now, this would have been in terms of the actual mass, right? So what was the mass that you've had, okay, that you've carried through there? Now, if you wanted to talk about the amount of time, so the half-life times, okay, then on a time scale, the half-life period, okay, or the half-life constant is going to remain the same. So how much time does it take to go to halfway point? So here is the actual equation that we have, and I just want to show you where this comes from. So this equation for half-life comes from the following. So here is, okay, the initial amount. So this is the initial mass. Now, sometimes amount, they'll write it as an A. So don't be surprised. You can certainly see this as written as A final is equal to A initial, okay? And then the half-life, okay, which is 50% of whatever number of half-lives that has carried out. So in here, I have a starting point, okay? And then I have the final amount of mass which remains. N represents the number of half-lives that you would have. Now, what is that? Well, what that is, so within here, so notice N, okay? So you can write this out in one of two ways. You can just fully put this into the equation. So if you write this in here, so instead of writing N, sometimes you'll see this T over the half-life time, where this T represents the amount of time that has passed by, and this TH represents one half-life time, whatever that might be, okay, within here. So if you take this on a time scale, so this is how it works. So here is, let's imagine, okay, that this is my time scale, but this would be the amount of half-lives. So how many half-lives have passed? Let's say one half-life has passed. This would have been a result of 50% of what you started. A second half-life would have passed. You would have been left with 25% of what you've started. A third half-life, you would have been left with 12.5%, okay, with what you started, and so on. And this continues on, okay, as you're carrying through. So within here, this would have been 6.25% of what you've started. That's what you have carrying forward, all right? And now, if you map this on, so if you take this entire thing, and now you scale it back in, okay, so within here, and you scale it with respect to time. So if this is time, okay, and you started at time 0, so this right here, which is your first half-life, this would have been T 1/2, okay, or TH, which I have in the formula, so whichever one you like to use. So that means how long did it take for this to decrease by 50%? This over here would have been 2 half-lives, and this would have been 3 half-lives, okay? And as you're carrying forward, this would have been 4 half-lives throughout, all right? Now, let's take a look and map this out, okay, with some examples, all right? So let's take a look how this particular item works. Now, as you jump in, okay, so within this, I just want to show you this. Why does this come up with a half? Like, where does this half? Obviously, we say half-life. But what this comes from is the fact that you start with 100% initially. And in exponential decay, what you're doing is you're saying, okay, if you decay this by 50%, notice then what you're going to be left with is 50%. And 50% in fraction form is 1/2. And that's exactly where this comes from. So half-life is where the decay is basically 50% or half of what you have started with. And now this n, okay, that you see in here just means how many half-lives have actually passed by. So let's see this, okay, through an example in here. So here's the first example, which relates it back to carbon. So carbon dating, okay, which is something maybe you've heard of, is sometimes used to determine the age of an organism's artifact. Now assume half-life time is, okay, and notice that it's a very long time, at least in this case. For carbon, it is 5,730 years, approximately. So that's the half-life time. So that means whatever you start off with in carbon, 5,730 years later, okay, give or take, you're going to have half of the amount of this parent, okay, atom within here, okay, so remaining from the initial amount, okay, that you've had. So now here's a question. After 10,000 years, what percent of the original carbon would remain? Okay, so what percent would remain? So now, if we map this out into a timeline, so within here, so if I put a timeline in here, and I say, okay, well, it takes, so this would have been 1 half-life, which is 5,730 years, okay? So this is all time in years. 2 half-lives, okay, would have been twice as much. So 5,730 times 2, okay, so that means, okay, so within, if I have that, this would have been 11, okay, 460 years, okay, so this is all in years. Now, if I look at this, and this says 10,000, okay, so in terms of 10,000, so it looks like maybe it's somewhere over here, right? So it's going to be, as you can see there, definitely not as many half-lives, okay, as we would want to be able to have. So how many half-lives is that? Well, in order to obtain that, your half-life, okay, so the number of half-lives you have, you take your total time divided by the half-life time. In this case, it's 10,000 years divided by 5,730 years. So if I take these two, so this would have been 10,000, 1, 2, 3, divided by 5,730. And this is approximately 1.745, 2. Okay, and this is the number of half-lives that have passed by for this. So if you want to know what percent, okay, remains from the original, we have to use the equation. So M final is equal to M initial, the half-life, okay, of how many, so this is N, so we're going to be plugging this right into there. Now, what are we starting off with? If mass is not given, then what I typically recommend when they're doing percents, just say 100. Because 100 means you're started off with 100%, right? Now this is in mass, so it would be, let's say, 100 grams or 100 kilograms, it doesn't matter. But whatever you get, okay, you can now obtain it because it's going to scale. So 100 is a really nice number to work with when you're being asked for percent, because 100% means the total starting point. So now I'm going to substitute this back in. You can take the decimal, or you can literally substitute the actual exponent as it is if you don't want to be carrying all of those decimal places. And now we can find out exactly what that is. So 100 multiplied by, now this is 0.5, which is a half, to the exponent. Okay, so I'm going to put it to the exponent. I'll put it in brackets. Okay, and I'll actually enter it, okay, within here so that I'm not entering those unnecessary decimal places. There you have it. So this is going to be 29.829, etc. Okay, as you're going through. So let's round this off. I'm going to round it to approximately, say this will be 30. So what does this mean? You started with 100 and now you are approximately at 30 or 29.8, etc. So this means about 30% remains, okay, of carbon 14 from the initial amount. So that means about 70% has changed into that nitrogen. That's what it is. Now, how many half-lives was that? It was 1.7452 half-lives. All right, so this is what you have. Now, what I also want to be able to show you is we can graph this, and it beautifully captures this exactly and shows us what is happening along, okay, with regards to these half-lives. So let me pull up decimals. All right, so here's decimals, and I'm going to, plot this out for us. So this is MF is equal to, I'm going to put M, okay, I. And this I, so this is multiplied by, I'll put 1 over 2. Okay, this is all in brackets. Okay, to the. Now, this depends on how you want to be able to graph this. If you want to graph it with respect to N, okay, so you can certainly do that, okay, up above there. And that will tell you with regards to half-lives. If you want it to graph it with respect to, so if you take this with respect to time, then you're going to have to put T over whatever the half-life is. Now, this was 5730 for us. So I'm going to do it with respect to time, right? So here, let's map these out. My initial, so let's say 100%, okay? And then my timeline, okay? So within here, I'm not going to map anything because I'm going to make this a variable. So let's take a look and see, okay, if this actually will scale out for us, okay, as you're going through. Now, because we're scaling on the years, so it's going to be thousands of years, time, okay, we're going to make greater than 0, all right? So let's see what this is, and I want to be able to scale this back in, okay? And notice that if I keep zooming out, it beautifully looks like an exponential. So starting from 100. And we mapped it, this was for, I guess, T, okay, which was equal to 10,000, right? So that's what we had it at. Okay, so if T equals 10,000, notice we get 29.829, okay, if I substitute it in. So you can see that in the decimals, okay, in there. So that's what we had. And we can drive this in and we can get to that point. So how many years, if you're going through there, okay, so what would it be? Now, 10,000, so 10,000 is going to be somewhere along here. There you go. Okay, so it's just about there. There we go. I just passed it. So it's somewhere along in here. So you can see the exponential decay continuing all the way through. All right, so that's one of the examples within here. Here's another example, okay, which is a neat example. So this is aluminum 26, which often is actually measuring kind of the age of kind of interstellar debris, so external debris outside of the Earth. So aluminum 26 goes through the following nuclear reactions. So it tells you it changes to magnesium, okay, and its half-life is rather long, right? So this is the radiation, okay, that we have that takes place. So it's it's 700 over 700,000 years, okay, for it to decay by half. Now, A, what percent of a rock would remain after 10 half-lives? All right, well, so 10 half-lives, so that's quite a long period of time, but as you know, so our galaxies are rather old. So within here, so if I wanted to take A, and I want to know, so this is n is equal to 10, so that's my half-lives. Again, my initial amount, so what percent, whenever they ask that, it's definitely worth your shot just to say 100, and it doesn't matter what it is, grams, kilograms, whatever unit you choose. All right, just start with 100 because that is, okay, a nice rounded number so that you don't have to figure that out. Okay, MF, we're not sure. And now if you substitute this in, MF is equal to, so this is MI, half, okay, of this is 10, okay, this was 100. So now we can plug this all back in into our calculator. So this is 100 multiplied by 0.5 to the 10 in there. And notice very little. So this is, whoops, okay, so this is what we have, 0.09765, etc. All right, okay, so within there. Now, let's round this off, okay, so this is approximately 0.009, I guess 8, okay, I'm going to round it off to two significant figures. And this would have been percent of the original. So from 100% of what you started, now you only have this much. Okay, so after 10 half-lives, okay, this practically disappears, right? So it's almost non-existent. Okay, so that's what we would have in there. Okay, so that's what happens. The more half-lives obviously just keep shrinking by half, by half, by half. And it continues on, okay, to break down. And you can see this, because if you stay and you say 100, well, divided by 2, that's 1 half-life. Divided by 2, that's another half-life, okay, so that's 2 half-lives. Divided by 2, that's 3. Divided by 2, that's 4, okay, that's 5. This is 6. Okay, this is 7, okay, this is 8, okay, this is 9, and this is 10, right? And there you have it. Now you could, of course, do it by exponents, which is much, much faster, and the formula itself. So that was part A. Now what about part B? If a rock from outer space has only 17% of its original aluminum, 26, right? So from that reaction, then what is the age of the rock? Ooh, so that's a really good question. So within here, so for part B, we have the following. We do not know what N is, okay? We'll assume that the initial amount was 100 because it says the final was 17%, which would have been about 17, let's say, grams of the original 100 that we had. So now how do we find this? Because if we take this into our formula, so we're going to get M final, which is 17, equals, okay, the initial mass. This is going to be 1/2. And then we don't know what N is, right? Now, N, of course, is T divided by the half-life. Now, we know what the half-life time is, which is 720, 000, okay? So if we find N, so if we can find this, we can substitute it in there and then we can find T, which is how long would that be? All right, so how do we do this? How do we solve for exponents? Now, I can certainly graph this, and then through graphing, I can find out what N is, right? So when do we get to 17? So I can approximate that. That's one way. So let me pop up decimals in here, okay? And I'm going to take that in. So here, let's put it in. I'm going to take this out. And now my MF, okay, so this is 100. I'm going to go back in here, and instead, okay, of doing this, I'm going to just call this N. And now, okay, so right there, so I'm going to go and start in there. So this is N, this is for N greater than 0. Okay, let's plug this back in. Okay, let's see what we get. All right, so within there, here's my exponential. Okay, so I'm just zooming in here. So if you take this on, okay, and now you can start scanning in there. So you want to get to 17%, okay? So 17% in here, okay? So that's 31, okay? 30, 29, 24. Okay, as you can see, there's your popping up. Oh, 17. So 17, okay, there you have it. So it's approximately 2.55 half-lives away, right? So we can do that by graphing and then seeing with this. Now, we don't want to be just doing graphing and seeing. We want to know, okay, kind of a better way to do this. And this is where you use logs, okay, which is the opposite of exponents. I'll put up a link up above there, okay, to a video on what are logs used for, okay, in mathematics. Well, this is going to be one of those items in here. So if you want to solve for this, then you're going to take, so this is going to be 17 divided by 100, so I'm just dividing by this, it is equal to, the 1.1/2 I'm going to just write as a decimal, okay, this is what we have. Now, in order to solve for that exponent, okay, you're going to have to take log of both of the sides, okay, so you're going to take log of both sides, okay, within there. So the equation here is that n is equal to, okay, this is going to be the log of one of the sides, which is 17/100, divided by, and this is log of 0.5. So you can watch the video, okay, before jumping into this, okay, and this is exactly what we get, okay, for n. So now n is equal to, so this, we will have n equals, okay, and I can plug all of this into the calculator to see. So second function, okay, so I'm going to just take in, so this is log. So log of, and I'm going to put 17/100, and then divided by log of 0.5. And that equals, so notice, 2.556, okay, 39, etc., which is exactly what we got, okay, when we were doing. So we got 2.55 because decimals was rounding. So that's how many half-lives, but that's only n. Now, we want to find out, so this is n, this is what we have. We need to find t, so we have to multiply by the how many years. So this, 720, 123, and this now tells you how many years that is. Okay, all right, so it's almost 2 million years, okay, so that would have been our answer, 1840603 years, and you can round to whatever it is that you like. Awesome question, okay, with regards to half-life. All right, so here's a final example for you, okay, so within this example, okay, we have gold, and now gold is undergoing beta negative decay, okay, as you can see there in the nuclear reaction equation. Now, part A, what is the half-life time of gold if 100 milligrams, okay, of gold has decayed to 1.834 milligrams in 15 days? Okay, so that's interesting and different than anything that we've seen so far. So what do they give us? They give us the initial mass, which is 100 milligrams. Okay, they tell us that this has decayed to 1.834 milligrams. And how long did this take? This took 15 days. And now we're supposed to find the half-life time. All right, so let's try it. So in the equation, what we have is the following. We have m final equals m initial, okay, times half. This is to the n. Now, of course, you can plug in t over th. Okay, I'm just going to find n first because I know the total time is 15. Okay, and then recall n is equal to the t, so total time divided by the half-life time. So if I find n and I have t, I can certainly find out what the half-life time is. Okay, so let's try that. So final is 1.834. initial is 100. This is 1/2 to the n. So by the same token, okay, in terms of solving for my exponent, so I'm going to get 1.834 divided by 100 is equal to 1/2 to the n, right there. And now, so my n is equal to, taking log of both sides, so I have log of 1.834 divided by 100, divided by, and this is log of 1/2. All right, so that's what I have right there. So what is this equal to? Okay, let's take out the calculator. Let's punch it back in. So log 1.834 divided by 100. Then divided by, this is log of 1/2 equals. So this is 5.76886, etc. half-lives. That's how many half-lives have passed by. That's my n. Now, in here, so because now I found this, which is on my calculator, this is 15. So now if I want to find TH, well, TH is going to be equal to T divided by N. All right, now this is 15, and then I have my N on my calculator. All right, so let's plug that in and let's see what it gives me. And there's your answer. So it's 2.6 days, okay? Because I was working with days, that's the half-life of gold, all right? So there you have it, okay? So that's another awesome question, okay, within there. To finalize this, where it says, what amount of gold was remaining after the first 5 days? Well, that is very simple. Now that we know the half-life, okay, time, which is 2.6 days. Okay, so now with respect to 5 days, we can just substitute this in. So let's do that all on our calculator. So we started off with 100 multiplied by 0.5 to the exponent. Now this is 5 days, so I'm going to put that in there, divided by your half-life, which is 2.6. Right there, that tells you how many half-lives have passed by. You hit equals, and you'll have about 26.369. Again, you can round to whatever it is that you like. Okay, so another awesome question, okay, within here. And these, okay, are questions with regards to half-life and the nuclear reactions. All right, thanks for watching. Okay, I encourage you to watch all the links, okay, that I posted up so that you're better familiar with half-life. Okay, see you in a future video. Bye, everybody.